One of the major triumphs of modern physics is relativity, for which we give the credit to Einstein. So, what is exactly the term relativity? Let's find out. So, as you can see, I am in a static car, and now I'm going to set this pendulum at oscillation, and let's calculate its time period. Now I'm in a moving car, and again I'm going to set this pendulum into oscillation, and then let's record its time period. The time period in both the cases is approximately 1.46 seconds. As we have seen that the time period for both the pendulums in oscillation in a static car and in a moving car is the same. This gives us the first basis of the special theory of relativity. That is, laws of physics are obeyed in all frames of references moving with constant velocities with respect to each other, that is, in all inertial frames. I and the car are moving at the same speed. So, from my point of view, the car is at rest. But you can see that the background is moving back. So, from the background point of view, we both are in motion. This proves that space is relative, it's not absolute. You can never say that an object is at motion or is at rest. It just depends on the relative point that we take. But light does not obey this. In 1865, James Clerk Maxwell showed that light is a form of electromagnetic wave and the speed of light is a universal constant. That is, no matter from where you observe, the speed of light will always be same. That is, 300,000 km per second. So, consider two cars moving in opposite directions with velocity v. Their relative velocity with respect to each other will be twice v. Now, consider two photons moving in opposite directions with velocity c. Their relative velocity will still be c. This led to the discovery of two startling yet realistic phenomena: time dilation and length contraction. Now, what is exactly time dilation? According to the special theory of relativity, the faster a velocity, the slower your time gets. Now, at the speed of light, the velocity is so high that the time will freeze. This happens in subatomic particles like muons, which form high up in the atmosphere. In Newtonian physics, these muons should never reach the ground because the decay time is not enough for them to reach the ground. But in reality, when we look from our frame of reference, the time gets dilated as they travel very fast and they easily reach the ground. From the muon's point of reference, its time remains same, but its distance contracts. We end this video with the famous equation of Einstein, E equals to mc squared.